All right, we'll go until it doesn't work anymore. 5.3 Euler's method. Again, this is a one-day lesson. It's your BC only method, or first of the BC only topics that we've talked about. Worksheets due when? Monday. Okay, good. Without reading all of that, blah, 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 I'm just going to kind of talk you through what Euler's method actually does. I think you'd rather do that than have me read it to you. So Euler's method is going to be something similar to what we've already done. If we have a function f of x and we are trying to approximate it at a particular value, but the function f of x, we either don't know what the equation is, or it's a function like the cube root of x or the natural log of x, something that's not really easy to evaluate at some funky x value. We could choose a center of approximation, call it x equals c. And what we've already done is used linearization. We have written the equation of a tangent line at that point. And what the tangent line enabled us to do then is to approximate f of x in a vicinity near x equals c. So if I was actually interested in this value of f of x, but it was too hard to compute, well, I could figure out what L of that value is. And the idea is near x equals c. On either side, we could approximate it to the left of the center of approximation. Near x equals c, L of x is a decent approximation of f of x. That's the whole idea behind linearization. The further away you go from the center, which is x equals c, where they actually have the exact same y value, the worse off you're going to be. In this case, we have an error that is by that amount. Now, what Leonhard Euler did is he says, you know what, why be content with using a single tangent line and having an error that could be potentially large? So what Leonhard Euler did is he came up with a brilliant idea of still using lines, still using linear equations, which have the advantage of being easy to compute. It's real easy to find the value of a linear equation, but he gave us better approximations by basically splitting up the distance that we're traveling from this x value to that x value there, partitioning it into smaller steps. So I'm going to illustrate his method just by breaking this up into 3 steps. And you could divide it up into however many steps you want. So it's kind of like what we did when we did Riemann sums. If we break the entire span of x up into, let's say, 3 steps of equal length, call them delta x, what Leonhard Euler said is, okay, since you have this point right here, and you have the derivative, you have the rate equation, let's go ahead and walk out along that tangent line, but not all the way to where we want to go. Let's just step out delta x. When I step out that far, what I could do is I could figure out what my new value is. Let's say we're starting at the point a comma b, just to make it easy. Then this new value here is going to be a plus delta x, and then b plus delta y. And I can figure out what that new point is if I know the slope of that line and the point that I started with. That's all I need to get the new point. He then proposes that we calculate the slope again at that new point, which is essentially going to give us a new tangent line. If I write the equation of the tangent line at the new point, it is going to kind of be closer to the curve. It might look something like that. And then he says, walk out along that new tangent line by delta x amount, calculate the new point, and then when you're at that new point, calculate another tangent line, which because of its vicinity to the actual function, it's going to have a slope that's closer to the actual slope, and then walk out along that final tangent line by some final amount. And what you have then is still an approximation for the function value at that point, but notice what has happened to the error. It's a lot smaller. So he basically says, let's use lines, but we'll walk out in tinier steps and we'll recalculate the slope along the way. And all the while, every time we calculate the slope, it's going to get us closer and closer and closer to what the actual tangent line is. That's the whole conceptual idea behind Euler's method. Now, what makes it a nice process is not the fact that it gives you a better approximation and it still uses linear calculations, but also the fact that it can be accomplished using however many delta, or however many steps you want to take, however small delta x needs to be to get as accurate as you want to be. You can actually take smaller steps, and you can get a better approximation. And if you're still not satisfied, break it into even more steps. And it's going to be a very systematic process, so there's yet another advantage to Euler's method. You can actually program a computer to do these calculations very, very easily. Okay? So that's the idea behind Euler's method. Now, the way to actually implement it, I'm going to show you a chart that you can use to accomplish Euler's method very systematically. Okay? Here's what the chart columns are going to be. You're going to be given an ordered pair at which to start. That's your x and y value. You're also going to be given a derivative equation, a rate equation. That's your next column. Once you have that set up, you know your x and y and your slope, what you're going to do is you're going to walk out along that first line. But you can't go out the entire slope amount because you're only going to go out some delta x amount. So as you move horizontally by delta x, you need to figure out at the rate of going up and over, how much does your y change? So your next column is delta y. And that delta y is just your slope that you calculated times the delta x. And it comes straight from your Algebra 1 slope equation. Delta y over delta x, if you solve it for delta y, you get that. Once you know how much your y changes as you march out along the line, you're going to be able to calculate what your new y value is. Your new y value, y sub new, is your old y value plus the incremental change in y. And then you're going to bring it back around over here, and then you're going to get your new x value by adding delta x. You're going to bring the new y value around, and you have your new ordered pair right here, and guess what? You're just going to repeat the process until you get where you need to get. So this is actually best illustrated through an actual example. Okay? Let's go ahead and try it out. Given the differential equation dy dx equals x minus 2, so there's the slope equation. It tells us what the slopes are in any kind of coordinate plane for any value of x. And if we're starting with the point 0, 5, it says find an approximation, there's your squiggle alert, for the function value y at 0.0 or 0.8x by using Euler's method with 2 equal steps. So you will be told to use Euler's method. It will actually say use Euler's method, or an Euler's method approximation is. And you're going to be given one of two things. You're either going to be told how many steps to take, in this case 2 equal steps, or you're going to be handed delta x, which implies how many steps to take. So let's go ahead and set up our table. You're going to have x, y, and then your slope, which I call m. Those are your first 3 columns. And then after that, you're going to have to compute what delta y is, and that's m times delta x. And then you're going to have your new y value. If you can memorize that, it's going to be real easy. Now, before we jump in and start, you do want to figure out your delta x. We are moving from x equals 0, that's our starting x value, to x equals 0.8. So let me write that off to the side. We're going from x equals 0 to x equals 0.8 with 2 equal steps. So what is each step going to have to be? 0.4. Very intuitive, right? Very intuitive. In general, it might not be so intuitive. So here's how you can easily determine your delta x if you're going from A to B. It's B minus A over N. You recognize that? That was your Riemann sum delta x, right? If you're going from A to B, the distance from A to B is B minus A. And if you're using N equal steps, you divide it by N. So for us, it's going to be, if you wanted to calculate it, 0.8 I'll get it, 0.8 minus 0 all over 2 equals 0.4. So there's your delta x. Now that you have your delta x, you can go ahead and drop in your original point. It's 0.5. And now we're ready to go. I need to figure out now what the slope is at my starting point. So I plug it into my derivative. The derivative here is only a function of x, which makes it nice. So what do you get when you plug in the 0.05 into x minus 2? You get negative 2. So that's the slope of the tangent line there. We're going to march out along that tangent line, but we're not going to go down 2 over 1 for a net loss of 2y units. We're only going to scoot over how far? 0.4. We're not going over full 1. We're only going over 0.4. So we're not going to change a full negative 2. We need to figure out how much we change when we only scooch over a fraction. So it's as simple as the slope that we just calculated, negative 2 times 0.4, which ends up giving you negative 0.8. We only go down 0.8 of a unit. Once you have the change in y, now you figure out your new y value. Your new y value is your old y value that you're starting with, 5, plus delta y, in this case minus 0.8, and that gives us 4.2. So we marched out along that first tangent line that had a slope of negative 2. We went over to the right 0.4 units, and we went down 0.8 units. So now we are standing at what ordered pair? Well, here's how you get your next row. You're going to add delta x to the old x value, which puts you now at 0.4, and you're going to bring the y coordinate from the last column over, which is 4.2. And there you are. Now you're standing essentially at that ordered pair. And you get to do it again. What? L? Oh. All right, let's do it again. I need to figure out what the slope is now. So it's 0.4 minus 2. What's 0.4 minus 2? Negative 1.6. Notice the slope is different. It's slightly larger now. And we now march out along that slope. Huh? Oh, okay. The slope is less steep, but it's actually increased, right? It's less negative. Okay. Now we find our new delta y, which is the slope we just calculated, times our delta x, which is 0.4. And if we type that in to our heads, we get negative 0.64. So we're inching out, again, horizontally by the same amount, 0.4, but we've only gone down now by 0.64 instead of a full 0.8. So the new y value is the old y value, negative 1.6. I'm sorry, I'm looking not far left enough. It's 4.2. And now we've gone down another 0.64. And so that gives us a 3.56. And we do it again. We add a delta x to our 0.4, and we get 0.8. And then we bring that y coordinate around over here, and we get 3.56. Now, do we do it again? No, we don't. We can, but we don't want to. It said to do it twice, do 2 steps. Here's the deal. We are now staring at the ordered pair right there that we want. We wanted to go to 0.8. We have 0.8 comma 3.56. So don't do it again. Now you can't just leave it in the table and walk away. You have to make some type of summative claim. It says to find an approximation for y of 0.8. So we just say, so y of 0.8 squiggles 3.56. Now, right here before lunch, before we go into part B, it is interesting to note, and this was brought up last period, what if we want to do a linearization? Linearization would be what I told you to start with, where we're taking the full step on one line. If you do Euler's method with one step, it becomes the same thing as writing the equation of the tangent line and plugging it into the new tangent line equation. Euler's method with one step is linearization. Let's see what that would look like. If I start at 0.5 and my slope is negative 2, well, what's my delta y? Well, it's delta x times m. But if I'm taking the full step from 0 to 0.8, instead of breaking it down, my delta x is 0.8. What's negative 2 times 0.8? Negative 1.6. And my new y value would be 5 minus 1.6, which is 3.4. And now I add my 0.8, and I'm at 0.8 comma 3.4. So 3.4 would be L of 0.8. If you were to write the equation of the tangent line, you would get 3.4. So Euler's method with one step is linearization. Now, according to our method, which one should be a more accurate value or approximation for the actual value at 0.8? 3.56. Euler's method in general is more accurate. And all we did on Euler's method is we took one extra step. If you wanted to get more accurate than 3.56, what could you do? Keep doing it. Make your delta x smaller, which means you're going to have more steps. The more steps you take, the more times you're calculating the tangent line, the closer you're going to be hugging the actual curve, the better approximation you get. Now, the calculations on Euler's method can be a slight bit tedious, especially when you have decimals, but all we're doing is multiplying and adding or subtracting, which is by far a lot easier than trying to approximate like cube roots or natural logs or something like that. Or in this case, approximating functions that we don't even know the equation for. So linearization, not a bad place to start. Euler improved upon that, okay? And he says you could still use lines, and you can now modify it to be as accurate as you care to be. You're not going to have to do Euler's method probably for any more than 4 steps. If you can do it for 4 steps, we're assuming you can do it for 400 steps, right? Yeah, you'll have the stamina and the ability to do that. But you'll also have a life outside of math, so we wouldn't make you do that. Well, some of y'all do, right? Okay. Anyway, we'll stop right there, and we'll pick up with B when we get back from lunch, and then we'll actually finish the whole section. So we're going to pick up steam, and we got example 2, 3, and 4 to go, and we'll be done. Worksheets due on Monday. Yeah. Have a great lunch.